recording this. Okay. So now let me hop over to the iPad. Okay. All right. So before diving into the rest of chapter 6, does anybody have any questions or concerns or anything from Monday? Anything on your mind? All right, well, then let's hop to it. Okay, so section 6.2 is about Bayes' rule. Now, the point of today is really just to play with some chance trees some more. I mean, the formal point is on here, right? That we'll formalize what we've been doing with chance trees and give some notation that we'll need in chapter 8 when we jump over to chapter 8. I should say again, though, that chapter 6 really is just chance trees. And the reason we're spending time a full week on it is just because getting used to chance trees just takes some time. So as we've seen, setting up an appropriate tree and then using the little pruning technique that we've been doing, that just takes some getting used to. Now, if you look at the homework, everything in the homework could have been done on our first day. So our first day of chapter 6 was last Friday. We could have just done one day of chapter 6 in theory and then moved on to chapter 8. Now, the first time I taught this class, I did do chapter 6 in one day. I thought to myself, oh, chance trees, that's one day of material, and then we'll move on. But that was a huge disaster because, as you've seen, right, they do take some getting used to, especially given the kinds of questions we want to answer. So that's why we spend a full week on it. So whatever that was 5 years ago or something, I did chapter 6 in one day, and then the homework came back really bad, and then the exam went terribly. And I thought to myself, those students, why didn't they learn anything? Whose fault is that? And initially, of course, I put the blame on them because I don't like to take responsibility for things. But of course, on further reflection, I realized, oh, you really can't do it in one day. What a terrible idea. So anyway, section 6.2, let's just start with some notation here. Make sure my Apple Pencil, I charged it like all night because yesterday I charged it and it didn't work. But anyway, okay, so here's some notation. And this notation, again, is fundamental to chapter 8. And this is really the only notation we need for today. So let's let A and B be possible outcomes or sets of possible outcomes of an experiment. So, you know, if you're going to roll a die, A could represent rolling an even number and B could represent rolling a 5, just whatever. If you flip a coin 10 times, A could represent the event that you flip 2 heads, and B could represent the event that you flip 8 or more heads. Anything like that. That's what A and B can be. Okay, so the main definition for today is the conditional probability of A given B, denoted like this. So in English, you read this as, this right here, you read it as the probability that A happens given or assuming that B happens. So assuming B occurs or assuming B has occurred, what is the probability of A? That is what that represents. So again, in English, this thing right here, that's the probability that A occurs, assuming that B occurs or has occurred. So the English is a bit clunky there. So that's the notation for today. So let's play with that for a second. So here in this example, A is the event that you roll 2 dice and you get an 8 or higher in the sum. And then B is the event that you roll 2 dice and you get a 5 or higher. Okay, so let me just start by asking you this. If somebody just asked you, hey, probability of A, just by itself. So I ask you, you're going to roll 2 dice, record the sum. What's the probability you get an 8 or higher? What's the answer there?
Can you repeat what you just said?
Yeah, so if I just ask you, you roll 2 dice and record the sum, what's the probability you roll an 8 or a higher? So you roll an 8 or a 9 or a 10 or 11, 12. What was that?
You can just use that little table below you, and it's like 15 out of however many that is.
Yeah, good. So here are all the ways to roll an 8, and then 9, 10, 11, 12, like that is all Trenton is saying right there. 15 ways to do that, 36 total ways. Is everybody okay with that? Just counting with that chart. So there's nothing special about that question, right? That I guess I could have asked you that on day 2 or something. Okay, now by contrast, if I say, oh, now I want to know the probability of A. So the probability of what comes after the of is still the same, 8 or higher, but you have to assume that you roll a 5 or higher. So in other words, I'm giving you some data. Basically, I'm telling you, for whatever reason, maybe these dice are loaded or something, I don't know. But for whatever reason, you know ahead of time you roll a 5 or higher, which means that this outcome here is dead now. You can't roll a sum of 2. These outcomes are dead now. Can't roll a sum of 3. These outcomes are dead now. You can't roll a sum of 4. So now I ask you, hey, what's the probability you get that 8 or higher that I cared about before, but given this extra piece of information that the dice are loaded somehow? What do you guys think about that? What would you write here? If you had to guess.
I mean, I guess if I had to guess, I'd probably multiply the probability of getting 8 and 5 together. But I obviously understand that's not correct.
Yeah, because you don't know you got a 5. I mean, yeah, you're right. So if somebody says like, hey, and actually, Trenton, you raise a good point here because when we get to chapter 8, we'll see there's a natural way to confuse these two probabilities. So as you said, they are different. So if somebody says, hey, the probability of getting 8 or higher and 5 or higher, you would do this. Assuming they're independent or whatever, right? But anyway, yeah, as you say though, this and is not the same as this given symbol. So maybe actually let's just revisit this this chart. So to get this probability here, we just did some counting. And when I say we, I guess I mean Trenton, right? Trenton counted the 15 outcomes corresponding to what we cared about, and there were 36 total outcomes in the chart. So if somebody tells you, oh, you know now you're going to get a 5 or higher. So these 6 things that I crossed out are crossed out, the little blue X marks there. If you did the same counting exercise, what would you write as a fraction over here?
(15/30).
Yeah, you'd say, well, there's 15 outcomes corresponding to what I care about. But now the sample space, if you like, we haven't used that language for a while, but the set of outcomes that are possible, there's only 30 of them. That's the idea of probability of something given some additional information. Basically, you can, what am I trying to say? You can prune or something. You can take your sample space that used to be bigger and you can toss some outcomes out because you're told they're not possible anymore. So that's the idea of this notation right here, this vertical bar. Probability of something, assuming something else, or given some additional information. So actually, let me clear the deck here. Let's just play around with this a little more. Let's say that A is still the same, but now B is the event you roll 6 or lower. So instead of 5 or higher, 6 or lower. What's the probability of A assuming B or given B? What's that probability now?
0.
Yeah, you guys agree with that? I'm telling you, hey, you're going to roll a 6 or lower. I'm just telling you, that's a data point. So again, maybe these dice are loaded somehow, who knows? But assuming you roll a 6 or lower, you're not going to roll an 8 or higher. It's impossible. So again, A used to have a relatively high probability, 15 out of 36, not particularly small, but if I give you some data and that data says, well, it's impossible now, then you update the probability. Okay, so that's the idea of probability of A given B. Any questions about that, issues? Okay, so again, Trenton brought up a good point, inadvertently, I think, but it's still a good point, that these two things, that probability and this probability, those are not the same thing. So, and actually, I've taught an introduction to stats course maybe twice, like 100 level course at different institutions. And that was this thing here was the most common error amongst those students when trying to deal with this conditional probability idea. They would be like, wait, probability of this and this? And I would have to keep saying, no, probability of this, assuming this. Probability of A given that B occurs, not probability of A and B occurring. It's a subtle difference, but it is a difference, as we've just seen. So that's one of the things that takes getting used to with this notation. And again, we'll be hitting this pretty heavily in chapter 8. Okay, so now let me return to sort of a classic conditional probability question. This is the kind of question you could have answered last Friday or Monday, but now I want to phrase it in terms of conditional probability and then formally present Bayes' rule. So this question is not new, but the way we're going to sort of frame it will be new. Okay, so I don't need to read all this to you, but you're going to take a diagnostic test. The test is reliable, but not completely reliable. This is true of like all tests, all medical tests pretty much. So if you have the disease, it'll tell you so 99% of the time. If you don't have the disease, it'll tell you do have it 2% of the time. So there's a 2% chance of a false positive, and there's a 1% chance of a false negative. So that's a pretty good test. Not perfect though. Okay, so suppose you're using this test on a population that's known to have a high rate of the disease. So before you even give somebody the test, there's a 50-50 shot they have the disease. So this kind of thing is also not uncommon. So if you test people for, say, what's it called, sickle cell anemia, that's just far more common amongst like African American populations than white populations. So if you go into the test, like if you go in saying like, well, I'm going to test a lot of African Americans with this, you just know that prior probability is way higher than on like the general population. Anyway, so you are one of these vulnerable people. You take the test, it comes back positive. So what's the probability you have the disease? Okay, so if we were in class, I would force you guys to write this and I would look at what you're doing. I still don't really understand how to make Zoom that interactive. So I'm just going to start drawing a tree and see if you agree with this. So initially, right, you either have the disease or you don't. And what are the probabilities on these branches?
Testing positive and testing negative.
Oh, sorry, what are the probabilities on the, so you're giving me this, the extra.
Oh, 1/2.
Yeah. Okay, so 0.5's there, but then as you say, Jacob, we can keep branching, right? So the 0.5 is a prior probability just based on our initial information. And then, yeah, as Jacob says, we either test positive or negative. So let's focus on this branch here, I guess. What's the probability there? Whoops.
99.99.
Yeah, 99%, right? Because there's a 1% chance that it'll tell you don't have it. Is that right? I'm looking back over this. Yeah, if you have the disease, it'll come back positive 99% probability. Okay, and then what's this branch here?
0.02.
0.02. So this is 0.98. Okay, so I want to, first of all, just use our, before we answer the question, I want to use our new notation, okay? So this branch right here, that 0.99, that 0.99 is this. It is the probability you test positive given that you have the disease. Oops, I'll spell it right. Now we've used this language a little bit in class, but not explicitly. So if you're in this branch right here, if you've made it here, you've only made it here because you have the disease. Like you had to have traversed this branch first, then made it to disease, then up like that. So that 99% number assumes you have the disease, and then it's the probability you test positive. So here's, in this new notation, here's how you'd write that. assuming I have the disease, the probability I come back positive is 99%. So again, there's a lot that can be confusing about this notation. One thing that is confusing is in English, I reverse the order in which I say things. So I say this, assuming I have the disease, probability of testing positive is 99%. That's how I say it in English. So in English, the order in which you say things out loud or the order in which I say things out loud are backwards. So, but the notation is what it is. It's completely standard. So we can't change it for this class. And then this right here, this 0.01, that's the probability I get a negative test, assuming I have the disease. And so on. So let's just do one more. This right here, 0.98 equals probability. I'm going to put a bar right here. So what goes right there? What's on the left-hand side of that bar?
Negative test result.
Yeah, probability the test came back negative, given what? What's right here?
Given that you don't have the
Yeah.
disease.
So assuming I don't have disease, there's a 98% chance it'll come back negative. So these branches that are branching off later in the tree, those are all conditional probabilities. 99% assume something happened before, as does the 1, 2, and 0.98. Now this right here, this 0.5, that's just the probability I don't have the disease right now. So that there's no information yet. There's no vertical bar saying like, oh, well, assuming blah, 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 right? And same thing with this 0.5. So all of that to say, what we're interested in right now, right? There's a lot you can get lost in the notation here, right? We're interested in this probability, the probability you have the disease. Okay, so let me come, I want to keep most of this in view. So let me come here. So here's what I actually care about. I care about the probability I have the disease. So again, what comes to the left of the bar is probability of. So after the preposition of, that comes before the bar. Okay, now given or assuming some data. So what is the data in this question that I can put right here?
Would it be a
Positive
positive
test
test?
result.
Yeah, good, right. So there's your data. What's the probability I have the disease given that my test came back positive, which it did. So there's a data point. So again, this is also stuff we did on Monday and the previous Friday, but now we're going to formalize it in this sort of notation and conditional probability language. And now my picture is getting to be kind of a mess here, but now we do precisely what we did last Friday. Let me clear off some of the highlighting maybe. Okay, so now we say, okay, I'll keep the yellow. Thank you. So now we just do what we've been doing. So what? We know the test came back positive. So these two branches here are the only live branches left. But we're interested in the probability I have the disease. So the branch I care about is this one. So just like we've been doing, we say, okay, here's the live branch corresponding to what I care about. And then here's the total weight of the tree after I prune, right? So I chop these off. Those are dead branches given the data I have. Plus 0.5, 0.02, like that. Is everybody okay with that? And now I don't know what this is off the top of my head, but if somebody has it from a calculator, you can tell me, or I can type it in a Wolfram. So if you get it ahead of me, you can yell it out. I'm just typing that fraction in. I get 99.99 798%. Does anybody disagree with that? Okay, so all that to say, I mean, the test came back positive. The probability you had the disease initially was 50%. So when the test comes back positive and the test is pretty reliable, it makes sense that your probability of having the disease goes up. And in this case, it goes up quite a bit, almost to 100%. So again, the point of this example is just to acknowledge that this notation, all this stuff, right? This notation, that's what we're doing as we're doing this problem. Okay, any questions on this? I'm kind of sad I'm recording this because this is a mess to look at. I'd rather not be a record of this mess that we're staring at, but. Okay, so all that to say in this previous example, Bayes' rule says this: probability that I have the disease assuming a positive test is, so let's see if we agree with this, in the numerator, probability the test comes back positive assuming I have the disease times probability of disease. So that's just this branch right here. Probability of disease is right here, and then here's that conditional probability right there, and then you have to divide by what's left, and what's left is, right, there's a match, this is down there, match, match, and then what's the other thing? What else is left? The other branch that left is, well, you have this data point of positive, but it could come back positive and you not have the disease. So that's this down here, this edge. So this is how Bayes formally described his rule. I mean, he didn't describe it in terms of disease or not, but this is how, if you open up, his original text from whatever it was, 1910 or something, this is how he phrases getting the probability of something you're interested in, like having a disease, given some data. There's your data. So this is how you update a probability given some data. That's what Bayes was interested in. Okay, so what I want you guys to do is do the exact same question, but let's say that now you're applying this diagnostic test to the general population. And like most diseases, right? Most diseases aren't particularly common. So pick a disease that you've heard of: cancer, breast cancer, maybe, pancreatic cancer, whatever. If you choose somebody at random from the population, the probability is pretty low that they have that. Even something like heart disease, there are like 330 million people in the US. And I'm just going to make up a number. So this is hashtag fake news for sure. But, maybe 15 million people have that. That's a lot of people. But still, relatively speaking, it's not that many compared to 330 million. It's not a super high percentage. Anyway, so redo the question where now your prior probability is not nearly as high as a coin flip. It's much less than a coin flip. So take 5 minutes, rebuild the tree, get a new answer, and we'll check back in like 5 minutes. Are you guys ready to talk about it? Should we set up the fraction? So you're still interested in the probability you have the disease. So the numerator is that branch. And the test came back positive. And then the total weight that's left in the tree, given a positive test, is this branch, this branch. Does anybody have the answer?
0.047%.
Wait, 0.047% or just
Percent.
like that?
Yeah.
Interesting. Okay. I mean, I knew it was small. I didn't remember how small it was. So like this as a decimal. Is that right?
Never mind, I was wrong. It's 0.47%.
0.47%. Okay. So let me just get rid of one of these zeros. Is that right?
Yeah.
Do people agree with that? Disagree with that? It's something like this. I just don't remember off the top of my head.
Yeah, I got 0.49, so it's the same difference.
Okay, that's fine. Okay, well, that's not very big, is it? Right? Now, before, what happened? You took a 50-50 shot and raised it to basically guaranteed to 100%, more or less. But now, what did you do? You started with, this is what, 0.0001. That was your probability before. Now, notice the test told you something. It's not like you learned nothing. It's just you took a 0.0001 and turned it into a 0.0047. And that's an order of magnitude difference, right? You multiply the original probability got multiplied by 47. Is that right? So it made a difference, but still your probability of having the disease is very small. So this is a problem, some people think, with taking diagnostic tests, even ones that are reliable. This is a pretty reliable test, 99%, 98%, and just hitting a general population with it. Because what you're going to have happen is a ton of false positives will pop out. And so the context I've seen this argued about is with mammograms. So mammograms as a way of detecting breast cancer, this 0.99 is not a 0.99. It's like a 0.83 or something. It's actually much smaller. So it's still reliable, but it's not nearly as reliable. Anyway, so if you just start giving like every adult American woman a mammogram, you're just going to get like millions of false positives every year with the corresponding stress and stuff that accompanies that, right? Like if your mammogram comes back positive, I mean, I don't know about you people, that would stress me out quite a bit. But what you're going to be seeing is some like your initial probability of having breast cancer was probably pretty low. So then your probability now is still pretty low, bigger, but still pretty low. Anyway, so all that to say, here's some more practice with chance trees with now this additional notation. So any questions on those before we wrap up the section here? Okay, oh yeah, the other context where I think about this is airport security. So like a metal detector, or even, that thing that goes like, you hold your hands up and it's like, boom, boom. You guys know what I'm talking about?
Yeah,
Should I do it again? Boom.
Yeah.
yeah, for sure.
Yeah.
Maybe
Boom.
stand up and give us a demonstration.
Those are things are pretty accurate, but they're accurate on like this scale, like 99% of the time. If you have a gun, it'll say that you have a gun. But like maybe 98% of the time, you have something else that's not a gun, but it thinks you have one. So most people who go to the airport don't carry guns, So if you just start like randomly testing people, you're going to get a very, very low hit rate of people with guns. Now, obviously, some people do. This example is in my head because my uncle has actually twice gotten in trouble for guns at the airport. One time, his kid accidentally packed a what do you call it, a pop gun pistol. That'll get you in trouble at that checkpoint. And one time, my uncle accidentally himself, in his carry-on, had a loaded handgun. Now, that'll get you in trouble, I think. So anyway, so my family history aside, there's a very small prior probability of somebody having a gun. And those woom woom whoosh whoosh machines, they return a ton of false positives all the time. So I don't know. Now, in my uncle's case, he was taken to some back room and interviewed, but he still made his flight, which I think is very suspicious. If you bring a loaded handgun to the airport, should you still make your flight? I don't know. Probably not. He did lose his, what's that status you get? Like you can cut the line, whatever that thing is. He lost that status. So
Priority flyer.
Yeah. He's no longer a priority flyer because he tried to sneak a loaded handgun onto his flight. So I guess that's an appropriate punishment. Anyway, all that aside, let me just conclude the section by pointing this out. One of the punchlines of these examples is that you have to keep track of the underlying proportions between various categories of people or objects when you're thinking about probabilities. So in this first example, 50% of your population had the disease, so it made sense to run this test and then interpret the results properly. With something like this scenario, right, where the underlying proportion of the population is only 1 in 10,000 who have the disease, you have to be much more careful about applying this test. So there are lots of other ways in which you should worry about underlying proportions. There are many other examples. I've listed a few here. These are just some of my favorites to stick out, right? So this is true. 10% of traffic, although it's probably gone down recently, but 10% of traffic accidents are caused by drunk drivers. So the vast, vast majority of traffic accidents are caused by people who weren't drunk. So if you're being really naive and not careful, and none of you would make this mistake here because this one's so obvious, but if you're being naive, you could be like, oh, I guess driving drunk is somehow safer, which is obviously a bad conclusion. But somebody just articulate, like, if you're keeping in mind underlying proportions here. So smack down the person who says this. What's wrong with their logic?
How many people drive drunk versus how many people drive sober?
Yeah, right. Like 99 point whatever % of drivers aren't drunk, So if you keep the underlying proportions in mind, you won't make a mistake like that. Here's one that's a little more subtle. I've heard this claim many times, even though it's the same kind of idea. Oh, no, sorry, not this next one, the one after that. But anyway, there are way more accidents during rush hour than during non-rush hour. So, we can just conclude, right, that non-rush hour times are safer than rush hour. But to Zach's point, I mean, there are just more people driving at rush hour than non-rush hour. So there's an underlying proportion issue. This one is the one I was thinking of. Have you all heard this claim? I used to hear this a lot for some reason, that driving close to your home is more dangerous than driving away from your home because way more traffic accidents occur there. So that might be true, I guess I should say, right? We don't know that this is a bad claim, but what's sort of like the logical issue with this?
A lot more people drive around their home.
Yeah, much of your driving is around your home, right? Like my neighbor, he works within 10 miles of his house. I don't know that he ever drives more than 10 miles from his house, right? So like if most people most of the time are driving close to their house, then of course more accidents will occur there. Now this last, go ahead.
Considering that considering that campus is several hours or a couple hours away from my home, I should be pretty hundreds of miles away from my home. I should be pretty safe.
Yeah, you're set. Yeah. Yeah, so no worries for you until you get to campus, I guess. Then you got to be careful. This last example I want to show you, because of my own personal shame. I fell for this. Okay, I fell for this when I was teaching this course. So here we can all publicly shame and I guess laugh at me. But there are these Geico commercials, and they'll always end by some authoritative voice saying, customers who switch to Geico save $600 or more on average, something like that.
And to be fair, their commercials are hilarious.
Yeah. So they reel you in with the gecko and their whatever their comedy bits.
It's what you do.
Yeah, right. So anyway, I was like, oh, well, I should check that out, because if people, I interpreted that statement to mean this. This is me in my own head here. Oh, if I switch to Geico, I should expect to save money, or there's a high probability I'll save money, I thought. So then I call up Geico and I talk to the gecko and I say, well, what's my quote? And my quote was like $300 more expensive than my current insurance. And I was shocked. I thought, no, wait a second. I was expecting to save money. I was thinking with a high probability I would save money, but they're quoting me $300 more than I'm paying. What's the deal with all that? So my question to you is, where was my error in logic, and why should I be ashamed of myself?
Because you're not average.
That's certainly true. There's no denying that. That actually wasn't my error in logic, though.
Where do most people who switch to Geico, where do they start? Like, what car insurance do they start at?
It actually doesn't matter for seeing the error in logic here. So sorry, let me be more explicit. So they're saying this, which is not a lie, by the way. They're not lying or anything. And so I took that to mean, oh, high probability of saving money if I switch to them. So this arrow right here, that's a sad logic error. But why? And there's like an underlying population issue, or perhaps an underlying proportion issue. And actually, let me say it like this. This green statement here, what population of people are they referring to there?
The people who actually switch.
People who switched, right? Now, why would you switch?
Because of those hilarious commercials.
Because your price is lower.
Yeah, because maybe because of the commercials, but probably because they're saving you money. So people like me who called them and they said, "Oh, it's going to cost you $300 more." I'm not switching. Why would I do that? So their underlying population are people who switched. So every insurance company can make claims like this. Hey, of the people who switch, those people save money. Well, of course, if you think about it, right? That's why they're switching. But there's a probably actually much larger population out there who wouldn't save money. And I just happen to be in that population. So you don't know until you see the population data or something, but like in my head, I was missing this Venn diagram, like people who would save money by switching. And then I'm over here. This is probably a much bigger slice of the population. I lost track of that. I was so eager to jump on the Gecko bandwagon and save myself, whatever, $600. So again, these kinds of errors can happen to anybody, even people who generally speaking know what they're doing when it comes to math and money, So anyway, if you think about chance trees, and in particular, think about this punchline that, you really need to think about, why did I scribble on that? You really need to think about the underlying proportions inside the population. You can avoid logic errors like this. So again, this one here, we all laugh at. We're like, oh, that's obviously silly. I see the logic there. But I laughed at that, and then I made this mistake here. So shame on me, I guess, right? So you have to be careful. Okay, so that's actually the end of chapter 6. We've now played with chance trees for a full week. I think we've gotten relatively comfortable with them, and especially with the sort of pruning idea, and now with this notational way of framing things. So any questions or comments on that? Okay, well, Zoom high five, and I'll see you guys in person on Monday.